Hi everyone, my name is Zahra. Today I'm going to present our paper on end-to-end performance analysis of hardware acceleration for DBMS machine learning scoring. It is well known that big data is a reason behind the success of many companies, and it is becoming a challenge for them to use this big data in the most efficient way. That's where machine learning can help. An important platform to extract and analyze valuable information from big data is a database management system, DBMS for short. Enterprise DBMS already support ML services, and this enables ML applications to use the well-established capabilities of DBMS to efficiently manage and control access to large amount of data that are already stored in the DBMS. And it removes the need for users to maintain separate coherent copies of large data sets for traditional query processing and ML applications. But the problem is that DBMS ML operations are significantly more compute intensive than the traditional relational operations. So specialized hardware such as GPU and FPGAs are needed to accelerate these operations. In this figure, you can see a list of hardware backends that we can use to run our application on. There is a full spectrum from highly flexible to highly efficient hardwares. So here, CPUs are the most flexible ones. You can run any algorithm on them. And at the other end, we have ASICs that are the most energy efficient one. So in our work, we used FPGAs because they are closer to ASICs from energy efficiency perspective and closer to CPUs from programmability and flexibility point of views. We also compared the Fpga results with CPU and GPU ones. This figure shows the best performing hardware backend among CPU, GPU, FPGA for the ML scoring operation of a random forest model for different combinations of data set size and model complexity. As you can see in the color chart, sometimes using an accelerator is not efficient, although hardware accelerators are designed to speed up computations. This happens when we look at the bigger picture and consider the end-to-end application performance, and when we take into account all the overheads of communicating with the accelerator to offload the task on it. It includes the overhead of data copy and the overhead of invoking different application pipeline stages. Another interesting point that can be seen in this figure is that when hardware acceleration is beneficial, the best accelerator to use depends on the data size and model complexity. There are so many FPGA-based ML acceleration solutions, but most of them only focus on the computations on the FPGA and the speed up of the offloaded inference task. They don't consider the communication or offloading overheads between the FPGA and CPU in their performance analysis. Some works have explored FPGA utilization to accelerate the compute-intensive stages of pipeline applications. In these works, either the target application is different or they don't analyze the effects of different model complexities and data sets on the scoring speedup. Also, they don't compare the FPGA and GPU performance. There is also AI tax work, which emphasizes on the need for the end-to-end performance analysis of AI workloads. They find that storage and network bandwidths become major bottlenecks with increasing AI acceleration. The difference with our work is that they do not measure the scoring time breakdown for accelerators. So in our work, we focus on ML model scoring in SQL Server using its capability of executing users' Python scripts. This figure shows the high-level architecture of the analytics and scoring pipeline. Users submit analytic queries that invoke custom Python scripts that score ML models. SQL Server launches an external Python process to execute the script. This script involves pre-processing, scoring, post-processing, and returning of results. The scoring can happen either on the CPU or it can be offloaded to a PCIe-attached hardware accelerator. Users can score any ML model with SQL Server, but for our work, we focus on tree ensemble models and especially on the random forest model, which is one of the top models being used in a wide range of classification and regression applications. The right figure here shows an example decision tree model that consists of decision nodes and leaf nodes. Each decision node has a comparison attribute and a comparison value or threshold to choose either the left or right node in the next level, and each leaf node represents a scoring outcome. The parameters of all the decision trees in the forest are learned from training phase. And during scoring, an example input traverses all the trees from root to the leaf node according to the criteria of decision nodes, and the final outcome is average of each tree's prediction, or it is selected by a majority voting mechanism. So for our FPGA experiments, we are using Onyx random forest model, and since we need to send the model info to the FPGA for inference task, we extract the model info from Onyx graph and prepare a data structure which describes the tree, like including the tree number, tree depths, and nodes. Also, to encode the tree, we use a specific memory layout for the tree, and we have a specific format for each node. For a decision node, as you can see in the figure, we keep the left and right node indexes, feature index to the input sample, and the threshold that we need to compare the input feature with. But for the leaf node, We just need to keep the class ID or the output class. However, to make the memory indexing easier in the FPGA, we keep the width of the index and leaf node the same by putting a negative or a specific value in the leaf node empty fields. So here is a high-level view of our inference engine. So through the I/O units, we receive the input data and tree model from the CPU. Then we pass these inputs to the processing elements, each working on one of the trees in the forest. We overlap the input transfer and inference. This way, we don't need to store the entire input batch into the on-chip memory. Instead, we are calling the processing engine with multiple threads, each thread handling one of the inputs. So this way, different threads or inputs can get into the inference engine one cycle after the other. Then once we get the output class out of all the trees, we'll send it to a majority voting unit to get the final result. We write it back in the result memory, and once we have all the outputs, we'll transfer it back to the CPU side. For our experiments, we use two datasets with different number of data features. Iris is multi-class classification dataset with 4 features and 3 classes, and Higgs dataset, which is a binary classification dataset with 28 features. We used RF with 1 to 128 trees with 6 to 10 level, the maximum we could fit on a FPGA. Our hardware platform for CPU experiments is a 2-socket Intel Xeon processor with 26 cores per socket. For GPU experiments, we used NVIDIA Tesla P100. For our FPGA experiments, we used an Intel Stratix 10 and implemented random forest inference engine using Microsoft internal HLS tool. So I'll start discussing the results with the breakdown of FPGA prediction time, and later on we are going to use this end-to-end prediction time for our comparisons with GPU and CPU. There are 5 main time components in FPGA prediction time. There is the input transfer time, which is the time spent on transferring the required data for scoring to the FPGA. This data includes model information and records. In our implementation, there is an overlap between record transfer and scoring operation. So input transfer time is only the time spent on transferring the model information to the tree memory. Then we have FPGA setup time, which is the time CPU spends to set up the FPGA connection and call the inference engine. The green box is the actual scoring time on the FPGA. Then there is an overhead to signal the task completion back to the CPU using interrupt, and also the time to transfer the results back. The software overhead is also the rest of the time, which is mostly spent on calling different FPGA functions and passing input arguments in the software code. So here we have the inference time for one record. For models with 1 and 128 trees for both Iris and Higgs datasets. As you can see, since we have just one record, the inference time is very small, and the tree transfer time is the dominant time component. So using FPGAs is not beneficial in this scenario due to the offloading overhead. But here we increase the input size for 1 million to 1 million for the same model and datasets. As you can see, now the dominant time component is the inference time, and the other overheads are negligible. So in this scenario, offloading to an accelerator is beneficial, since the inference time is the main time component in the end-to-end prediction time, and an accelerator can greatly improve that. So here is a high-level view of this paper's findings. These numbers are all end-to-end scoring time on different hardwares. We have results for end-to-end application time or SQL time in later slides. In this figure, we show the Schmo plot for which backend among CPU, GPU, and FPGA gives us the best performance for a given combination of number of trees, x-axis, and number of records, y-axis, for both Iris and Higgs datasets. For each combination, we also plot the best achievable speedup as compared to the CPU. For example, if we take the right chart for Iris dataset for 1 million records and 128 trees, the green cell indicates that FPGA is the best performing backend, and it runs about 54 times faster than CPU. The bottommost row for Iris and Higgs tables shows the GPU speedup for 1 million records and different number of trees as compared to the CPU. So the main takeaway from this figure is that floating and scoring to an accelerator is not always the best choice. For a simple model, small number of trees or small number of records, for example, in the first 3 rows of in the tables, we don't get any performance benefit from floating the scoring to an accelerator because the offloading overhead is the dominant time component in the overall model scoring time. However, as the model complexity or the number of records increases, by offloading to an accelerator, we can get about 69 times speed up in the model scoring time. Another interesting point here is that since Higgs has more data features than Iris dataset, it generates larger models, even with a smaller number of records, 1K records in Higgs versus 10K in Iris. Offloading to an accelerator is beneficial. So here you can see the CPU, GPU, FPGA prediction time in millisecond, y-axis, based on different number of inputs, the x-axis. For the CPU experiments, we used both Onyx and scikit-learn models. Also, we tried Onyx model with 1 thread and 52 threaded CPU. All the graphs here are for Iris dataset. Top row graphs shows the results for random forest with 1 tree, and the bottom row graphs are the results for 128 trees with different maximum tree depth. As you can see, even with 1 tree, top row graphs, as the number of inputs increases, the FPGA and GPU speedups over CPU increases. Since here for 1 tree, scikit-learn is doing better than ONNX, I compared those results with GPU and FPGA ones. So in this case, FPGA is doing up to 4.5 times better than CPU, and GPU is also doing 7 times better than CPU. In the top right graph, the maximum tree level has increased, but the results are very close to 6 level 3. So it means that increasing the number of tree levels is not as effective on the prediction time as increasing the number of trees is. In the bottom graphs, as we increase the number of trees for the CPU, ONNX is doing better than scikit-learn this time. Also, 52 threaded CPU results is the lowest one. So I compared this one with the GPU and FPGA results. This time, by increasing model complexity, the number of trees, FPGA is doing about 7.2 times better than GPU and 54 times better than CPU. So it's showing that as the model gets more complex, whereas the number of input samples increases, FPGA is doing better than CPU, both CPU and GPU. We'll reason about this in the next slide. Okay, here we can see the results for a more complex dataset, HIGS, dataset with 28 features, and generate a more complex model. There is just 2 output classes for this dataset, and it is a binary classifier, so it is supported by Rapids library. We are adding Rapids here to the GPU experiment results. As you can see here, for 1 tree, both FPGA and GPU results are very close. But as the number of trees grows, FPGA results get better. And still, FPGA and GPU Hummingbird both are doing better than CPU for large input sizes. GPU Rapids is about 16.5 times, and FPGA is about 69 times faster than CPU. Here, FPGA is doing about 4.2 times better than GPU. This could be because as the model complexity, number of trees, or dataset size increases, on the GPU, we get more cache misses, which are very costly. However, on the FPGA side, we are putting all the required data for the computation into the on-chip RAM upfront, and there is no cache miss. The other reason is the control flow divergence across trees. In GPU, different threads which are processing different trees may follow divergent evaluation paths down the tree. And this gets worse when we increase the model complexity. Also, the other point here is about Rapids. It has a separate data preprocessing step to convert the NumPy array to CUDA data frame, which takes about 120 milliseconds. So that's why Rapids is not doing well for small data sizes, where the prediction time is less than this preprocessing time. But after 800K reports, it's getting a better results than Hummingbird and getting closer to FPGA. For throughput results, please refer to the paper. So, okay, let's talk a little bit about the application level overheads. In this graph, we can see the end-to-end SQL time for ML operations. The time components here are blue box, the preprocessing model time. In SQL, the models are stored as byte strings. And when we read this model from the SQL Server, we need to deserialize this byte string and convert it to a model object. And then there is the preprocessing data time, which is for converting input data frame from SQL Server to NumPy array, which is later on fed to the model prediction time function. Then there is the end-to-end prediction time in green. Then the Python invocation time, which includes the time taken for launching the external Python process, like creating a new process and then calling Python exec. The data transfer overhead is also the time spent on transferring the data in and out from SQL Server to the external Python process. So in the graph, the left bars are for IRIS dataset and right bars are for HIGS. The first 3 bars in each side shows the results for a simple model and data, 1 tree, 1 record. So as expected, we can see that the prediction time is very small for these bars, and the dominant elements are Python invocation time and the time it takes to deserialize the model. But as the input size and model complexity increase, for the CPU, the prediction time is dominant, but offloading the prediction to GPU or FPGA decreases this component, and this time the data transfer is becoming the dominant time component. So generally, the takeaway here is that to get a good end-to-end acceleration, we also need to accelerate other bottlenecks in the pipeline, bottlenecks other than prediction time, which is addressed by accelerators such as FPGA and GPU. These are mainly Python invocation. These bottlenecks are mainly Python invocation time and data transfer time. So as a summary, in this work, we studied the speed up and overheads for CPU, GPU, and FPGA acceleration for DBMS machine learning scoring. And we found that the benefits of scoring depends on hardware backend, model complexity, and dataset size. For models with lower complexity and for smaller data sizes, it is preferable to use CPU and not a dedicated accelerator for scoring. While for models with higher complexity and large data sizes, it is better to use FPGA-based accelerators for ML scoring. Also, these findings highlight the need for a runtime scheduler which selects the best performing hardware backend based on the input query parameters at runtime.